Hi folks, here we are again. So this is lesson number 9 and today we're going to look at specific heat capacity, what it means, how we calculate it. Okay, so busy lesson. Have a look at this slide and let's move straight on. Okay, although it's a busy lesson, we still need to recap on things we've learned in the last few lessons. This continual recap just helps move information to the right place so that you can recall it. Okay, so you put it into your working memory and your short-term memory, keep going over it, and that will help you in the exams. So here we go. We've got some 3-2-1 questions. Okay, have a go at those. They might have been printed off for you, or they'll be attached if you're doing this lesson remotely. Okay, so off you go, and we'll look at the answers in just a second. Okay, so on what two things does the elastic potential energy of an object like a spring depend on? So from the lesson, last lesson, spring constant and extension. Okay, because there's the formula. Now, you don't need to remember that one. You do need to use it, but it doesn't hurt to have a go. And what does the term spring constant mean? It means how stiff the spring or material that you're talking about it is. Here's a formula for kinetic energy. You do need to recall that one. And what unit is velocity measured in? Meters per second. And then here's a little calculation of gravitational potential energy. Stephen is diving from the 1.5 meter board. And therefore, if you use gravitational field strength to be 10 units per kilogram, he'll have an gravitational energy of 1080 joules. Okay, so over to this lesson then. Write down today's title. You might have been swimming at the beach. What do you notice about the temperature of the sand compared to the water? Now, let's just pretend it's been a hot, sunny day. Okay? And even if you thought the water was relatively warm, compared to the sand, what does it feel like? This is something to do with specific heat capacity. Okay, so you find that usually the sand is quite hot, but the water is always cooler. So why is that? Sometimes you feel like you can burn your feet on the sand. But you don't burn yourself as you go into the sea, into the water, do you? So this is all to do with specific heat capacity. So today, this is what we're going to be looking at. I'll leave you. You can pause the video if you want to have a look at that before we move on. Really important that you get the your definition sheet up to date. So this is the third one for this topic. Okay, the spellings are important, the definitions more so. Using the words correctly is the best thing to do, so make sure you've got that sheet with you. Okay, now, not the calming narrator with his calming voice, but this is a slightly different one. Watch the video all the way through. You'll have to pause this video and go on to the other PowerPoint, and you can pull off the link from there. Okay, so you watch that and come back and join me in a few minutes. Alright, so to take you through some of these points here then, if we've got water and sand and we put the same amount of energy into it, if we were able to measure the temperature of both at the end, what would have happened? So think back to that earlier slide where I asked you a very similar question. Same amount of energy being transferred into the water and sand. What happens? Do they reach the same temperature? No, they don't. We've got a small temperature rise of the water here after a hot sunny day, but a much larger temperature rise of the sand. That's why we can burn our feet on the sand. So transferring the same amount of energy by heating into some materials doesn't always get the same temperature rise out. So it actually depends on the material. Okay? All right. So if you compare water and cooking oil, and if we were in a lab we would be able to do this. Okay, so let's say the starting temperature of each is room temperature, so 20 degrees Celsius for both the water and the cooking oil. What would happen to the temperature of the water and the oil if they had identical heating from identical rings, heated for 1 minute? What do you think? Do you think they'd be the same temperature? Do you think they'd be different temperatures? Okay, well, in fact, this is what would happen. The water might possibly rise by, say, 30 degrees C, and the oil might rise by 60 degrees C, taking us from our initial 20 up to our final temperature of 80. In other words, it's easier to heat up the oil than it is the water. Okay, so if we transfer the same amount of energy in, we only get half the rise in temperature of the water, 30 compared to 60. So that tells us something about the specific heat capacity of these two materials. So what would we need to do to make the temperature the same then? What would we need to do to make the temperature the same, do you think? Okay, we would have to put twice as much energy into the water as the oil. Okay, that's what we would have to do to get them to rise to the same temperature. Okay, we'll come on to a definition of specific heat capacity shortly, but it's quite useful to have another think about this sort of thing. So the water's got twice the capacity to absorb and store energy from heating as the oil has. So materials vary quite widely. There's no specific pattern to all of this, although metals do tend to have low specific heat capacities. So all of these have got different specific heat capacities. So if you have a look at these values here, predict what you think will happen if the same amount of energy is transferred into each by heating. We get a much higher temperature rise if we put the same energy into copper than we do if we put it into water. Even rock has 4 times the rise in temperature than water does. Okay, so they all increase in temperature, but by different amounts. So if we said, well, we want to get the same temperature rise, how long would we have to heat for? And basically, because water has got 4 times, last time it increased by 4 times, silica rock increased by 4 times as much as the water. That means in order to get the same temperature rise, we would have to transfer 4 times as much energy into the water to get it to rise to the same temperature as the rock. So what we could say is that there's a higher heat capacity for water than there is for rock. Okay, it requires more energy to be transferred to heat it by the same amount. Right, we're coming on to our definition in a minute. So basically, don't worry about writing this down just now, I'll give you a chance in a minute. The amount of energy in joules needed to change the temperature by 1 degree Celsius is heat capacity. Okay, and this is illustrating our particles vibrating more kinetic energy. Okay, so if we're going to make a fair comparison between materials, we'd also need to use the same amount of materials. Okay, so when we're talking about specific heat capacity, we're talking about comparing the mass, the same mass of material. So get your pens out, because this is what I'd like you to write down. This is the definitions, the specific heat capacity of a substance. The specific heat capacity, the shorthand way of writing that is a C. Okay, it's the amount of energy in joules needed to change the temperature of 1 kilogram of the substance by 1 degree C. Okay? All right, so this is an equation. It is a select and apply equation, which means that you don't need to remember it, but you need to know how to use it. Okay? You work it out, specific heat capacity, because it's the energy transferred by heating divided by the mass of a substance and the temperature change. Now, if you look very carefully at the units, we've got energy in joules, mass in kilograms, and temperature change in degrees centigrade. That means that for specific heat capacity, the unit here, be careful with this one, it's a tricky one, it's joules per divided by kilograms degrees C. No extra line in here, please. Okay, these two are just multiplied by each other, as you can see in the equation here. So the shorthand is C for specific heat capacity, E for energy, M for mass, and this sign here means temperature change, change in temperature. That's the mass symbol there, the triangle, which means change, and that's the theta symbol there, which means the temperature change. Okay, that is given on the equation sheet, but it's given in a slightly different form. It's given in this form here. So it's given as energy transferred, there's the E, equals your mass times specific heat capacity times the temperature change. Right, over to some practice then. Okay, so make sure you pause the video and have this form written down, and away we go. Okay, so here's an example. How much energy is needed to increase the temperature of 6 kilograms of water by 80 degrees C? And they've given us the specific heat capacity of water, which is a huge number compared to other materials because it's really hard to heat water because it's got this high specific heat capacity. Everything's in the right units, that's worth checking. So there's the equation, just substitute in the numbers you need. Remember, we need to see the workings out. So let me show you. Okay, 6 kilograms times 4,200, that's our specific heat capacity, times 80 degrees C, and there's our answer with the units. Textbook work, okay, so make sure you've got that down as a worked example. Okay, so here's a couple for you to practice. So have a go at the questions here and pause the video while you do that. All right then, question number 1. Substituting in the numbers you know. Oops, where am I going to put that? Up there. Okay. No reason you have to turn it into kilojoules. I wouldn't. I'd be totally happy if you left it there, 125,430 joules. I wouldn't convert if you don't have to. Okay. Here, same equation. Okay. 5,106 joules. Again, no need to convert. Third question, what can you say about the specific heat capacity of water compared to other materials? So you're comparing. So you need to quote on what these numbers mean. If the number is big, it means it's got a high specific heat capacity compared to the other materials. That's exactly what I would say. It's unusually high specific heat capacity. It takes a lot more energy to heat up 1 kilogram by 1 degree C than other materials. Now, this is the equation substituted into a formula triangle in case that's your preferred way of working it out. All right, so let's just look at how we put it into the formula triangle. Energy equals mass times specific heat capacity times temperature change. This is the 3 things multiplied together here, so this is the larger part of the equation, so it goes in the bigger part of the triangle with change in thermal energy or just energy on the top there. Okay. All right, so let's have a look at some slightly trickier questions where you might not have to rearrange the equation, but you've got to look out for the units. All right, so on this one, what have we got to look out for? You're right, this 600 grams up here needs to be converted into kilograms first of all. Okay, off you go, have a go at that. All right, so convert 600 kilograms into grams first by dividing by 1,000. And you see that's this question that we had before, just made slightly trickier. Gold standard question. Okay, 8 kilograms of water is heated from 20 degrees Celsius to 40 degrees Celsius. They've supplied the specific heat capacity. What's tricky about this? Not much really, but you must remember you need to work out temperature change. Okay, so we've got our 40 minus our 20, which gives us our temperature change there. So there we go. Again, no need to convert it into kilojoules. Don't convert if you don't need to. And when you've done that one, there are lots of equation sheets for you to practice this one on. So pause the video, go off and have a practice of those, and then we'll just briefly look at a foundation and higher question. All right then, so here's a foundation question. Give you time to read it, have a go at it, pause the video, and then we'll look at the answers. Okay, substituting in the correct numbers. There you are, correct substitution, 1 mark, answer, 1 mark, units, 1 mark. 3 marks. Did you score all 3? Go back and green pen if you didn't. And here's a slightly harder question. So to heat the water in the tank from 50 to 58, the immersion heater transfers 4,032 kilojoules. Calculate the mass. So we've got to rearrange the equation, substitute the numbers in first of all. But first of all, we've got to turn our kilojoules into joules, and we've also got to work out our temperature change. Right, I've given you all the hints, taken away the hardness really. Off you go, have a go at that. Okay, so if you pause the video, here are your answers. The answer is 120. The answer was given in kilograms. The units were already specified there. So this is what the marks are for. I'll let you study that for a while because that's worth looking at. And that takes us to the end of the lesson.